Let's dive right into today's explainer. We're tracing the incredible journey of electrical energy. I'm talking about everything from a microscopic electromagnetic heartbeat all the way up to the massive global power grid. Today we're unpacking the hidden physics of electromagnetic oscillations and alternating current that literally light up our world.
Here's our roadmap. We'll start with the perfect heartbeat, then see how reality bites. Look at driving the system, the power of resonance, real-world power, and finally, scaling the grid.
All right, part 1. The perfect heartbeat, LC oscillations. To really wrap our heads around this, we have to start with a purely theoretical, frictionless setup, the ideal LC circuit. That just means a system with only two components, a capacitor storing electrical energy and an inductor storing magnetic energy.
The crucial thing here is this endless shuttling of energy back and forth. It represents a perfect electromagnetic heartbeat. Imagine the capacitor is fully charged. As it discharges, its electric field transfers energy into the inductor, building up a magnetic field. Once that capacitor is empty, the inductor's magnetic field collapses, pushing the current forward to recharge the capacitor in the exact opposite direction. The total energy? It stays completely constant. It's an infinite, perfectly balanced loop.
You know, we can actually compare this invisible circuit to something super physical, like a block bouncing on a spring. Just as that physical block constantly trades potential energy for kinetic energy, our LC oscillator constantly trades electrical energy for magnetic energy. The math and the physics are practically identical. It proves that invisible electrons and magnetic fields bounce back and forth just like a physical weight on a bouncy spring.
But, of course, part 2, reality bites with damped circuits. Let's introduce real-world physics here, because perfectly frictionless systems, they just don't exist outside of a textbook. By adding resistance, we transform our pristine LC circuit into a damped RLC circuit.
What happens is that the electromagnetic wave actually dies away over time. This is a process called damping. Every real-world wire and component has at least a little bit of resistance, and that resistance acts exactly like friction. It continuously drains the circuit's total electromagnetic energy, bleeding it off as thermal heat. So over time, those beautiful, high peaks of energy shrink down to absolutely nothing.
Which brings us to a massive engineering hurdle. If our system's heartbeat is fading out because of resistance, how do we possibly inject life back into this dying circuit? How do we keep the oscillation going so we can actually use it to do sustained, useful work?
That takes us to part 3, driving the system with alternating current. We need an external force to keep that rhythm alive. And the answer is alternating current, or AC. By bringing in an external AC driving force, something like a generator, we can continuously inject energy right back into the system. This external force pushes and pulls the electrons in this perfect sinusoidal rhythm, exactly replacing the energy lost to thermal heat. We call these forced oscillations, and they're exactly what keeps those neon waveforms glowing bright and steady on our screens and powering our homes.
Moving on to part 4, the power of resonance. This is where things get truly fascinating. What happens when that driving force perfectly matches the circuit's own internal rhythm?
Well, when the external driving angular frequency perfectly matches the circuit's natural angular frequency, the circuit achieves resonance. Right at this sweet spot, the inductive reactance perfectly cancels out the capacitive reactance. Basically, the internal hurdles of the circuit neutralize each other. The result? The current amplitude surges to its absolute maximum. The current and the external voltage are perfectly in phase, marching in exact lockstep.
Think of it like perfectly timing your pushes on a playground swing. Matching the natural frequency in any physical or electrical system unleashes just staggering raw power. Pushing that swing at exactly the right moment makes it go higher and higher. When resonance goes unchecked in mechanical systems, the physical consequences of those forced oscillations can literally tear structures apart. But in an electrical circuit, resonance gives us the maximum possible current, which is incredibly useful for things like tuning radios or maximizing power transfer, as long as it's properly managed.
Part 5, real-world power and RMS. So now that we've maximized our circuit's potential and we know how to drive it, we have to figure out how to actually measure and distribute this oscillating power.
Here's the tricky part about alternating current. The voltage and current are constantly swinging between positive and negative. If you took a simple average over time, it would literally be 0. Because of this, engineers use root mean square or RMS values. We take the peak amplitude and divide it by the square root of 2.
This clever trick gives us a meaningful number, allowing us to calculate the true average rate of energy dissipation, so we can treat AC power just like standard DC power in our calculations. Fun fact, when you hear that your wall outlet is 120 volts, you're actually hearing its RMS value. Finally, Part 6, Transformers and Scaling the Grid. We have to scale this microscopic RLC circuit up to the massive, interconnected global power grid. How on earth do we get this energy from a power plant hundreds of miles away to your toaster without losing it all along the way?
It all boils down to the general energy transmission rule. To transport power safely and efficiently, you absolutely must transmit at the highest possible voltage and the lowest possible current. Why? Because the thermal energy lost in the transmission wires, known as ohmic losses, are proportional to the square of the current. So keeping that current low is the absolute key to grid efficiency.
To put that into perspective, let's look at the math. If a power plant tried to transmit high current, say 1,000 amps, without significantly stepping up the voltage, a staggering 60% of their energy could be entirely wasted as heat before it ever reached your home. That is completely unsustainable.
Enter the transformer, which brilliantly solves this efficiency problem using simple magnetic induction. A transformer takes alternating current into its primary coil, which creates an oscillating magnetic field in an iron core. This field then induces a brand new voltage in a secondary coil. But just changing the ratio of the wire turns between the two coils, power companies can step up the voltage to massive levels for cross-country transmission, keeping the current super low. Then, local transformers step it right back down to a safe 120 volts before it enters your house.
But the physics we're decoding today extends far beyond the electrical grid. As the science shows us, changing electric fields create magnetic fields, and changing magnetic fields create electric fields. These exact same continuous cycles of electromagnetic induction are what creates light waves. They travel endlessly through the vacuum of space, entirely self-sustaining, to warm our planet and make life itself possible. I hope this explainer has illuminated the hidden physics of your world. From a simple oscillating circuit to the vast power grids and the light from our sun, it's all connected by these elegant, invisible rules. As these fields oscillate endlessly around you right now, it leaves us with one final thought. What other unseen physical forces are secretly shaping your reality at this very moment?